Okay.
Thanks, Cheryl. Today's speaker is Dr. Kimfet Dualdebrahan. Kimfet is no stranger to HAO. He's been here multiple times because he got his PhD from Addis Ababa University in 2018, but under the supervision of me. Since he got his PhD, Kimfet has been working in the physics department at Axum University, teaching and mentoring graduate students, and he has an assistant professor position there. Kimfet's work focuses on the solar dynamo. He studies the impact of convergent flows into active regions on the global solar magnetic activity. He does this in the framework of a three-dimensional Babcock-Leighton solar dynamo model. And Kimfet is currently visiting HAO. He's been here for a few months now, and he's working with Sarah Gibbs. They are studying the coronal magnetic field evolution that results from simulated photospheric magnetic fields from his dynamo simulation. So I'm going to let him start his talk today.
Thank you, Rebecca. Thank you. The coordinators, thank you, Shred. I'm going to present the magnetic field dependent inflows towards this active region. There are many impact on a three-dimensional Babcock-Leighton solar dynamos. So here are the presentation outlines. I'm going to present introduction, which is a very brief introduction. Is about solar magnetic activity, and it is at Earth, solar cycle, and solar dynamo. Then I will present the stable model development, like the flex emergence spot maker algorithm, and then modeling the bipolar magnetic active region inflows. These are the inflow. I will be able to present the observation implication for the dynamo, mathematical formulation of the inflow field, and then I am going to present the simulation results of the evolution of two bipolar magnetic active regions and their consequence on the meridional circulation and the polar field buildup. This will be from two types of dynamo quenching, the simulation. And then, as a brief, I'm going to present a future work or a plan for the future work. So, I know, as we all know, the sun is an active star whose magnetism has a direct impact on the Earth and our modern technological society. Then, as we can see here, the solar eruption towards the Earth, it's good to understand this one is essential to study this magnetic activity and magnetic cycles of the sun. So, saying this, how is this eruption happens, or how the flex emergence happens? As we can see here, the magnetic field lines line up in the solar interior. When the magnetic flux gets strong, they emerge to the solar surface, which is the photosphere. These are the manifestation of the flex emergence. In their simplest form, bipolar magnetic active regions. In this talk, I'm going to interchangeably use BMR, sunspot, and active region. So, as you can see here, the full disk magnetogram that shows the line of sight of the density of the the flex density, magnetic flex density, and these are as sunspots or bipolar magnetic regions. As we can see here, these are as leading and following spots. The leading spot is slightly closer to the equator, and the following is farthest from the equator. That means so these are, if we make a line, if we stretch a line between the center of the magnetic polarities, the leading and the following, there is a tilt angle that joins the line between the following and leading spot. This tilt angle is actually the Joyce law. So these spots with opposite magnetic field, with opposite magnetic polarity, are changed with hemisphere and solar cycle. That is the halo polarity. Okay. The solar activity is associated with the sunspots. The number of sunspots that appears with a cyclic variation approximately with 11 years, that is the solar cycle, and the number of spots increase and decrease with solar cycle actually, and as we can see here. This sunspot cycle is best for the manifestation of solar magnetic cycles. And here that shows the emergence of sunspots that starts in both hemispheres actually. These are the solar latitude, location of solar latitude of emergence of spots. They start to emerge at a mid-latitude and they, through time, they progress towards the equator. This is the sunspot region of the last 22 cycles. That shows the butterfly diagram, which is the striking pattern of the merging of sunspots. Now, let's see the Babcock-Leighton solar dynamo. This is the paradigm leading to determine the magnetic cycles and the solar dynamo, actually, the Babcock-Leighton dynamo, and the sunspots are linked to the internal dynamo. Actually, the sunspots that we have seen emerging to the surface are connected or linked to the internal dynamo. As we can see here, this is the polarial field and shared by the differential rotation, and toroidal field is created due to the differential rotation. When the toroidal field at the in the interior becomes strong, it becomes buoyant and it gets twisted due to the Coriolis force and actually the effect of differential rotation and the Coriolis force. And when the sunspots emerge, they become two dots with opposite polarity due to the differential rotation, and the meridional circulation actually transported to the pole and submerged down, which creates opposite magnetic field to the beginning of air, that is the polarial field. And this shows that the cycling fashion of the creation or the maintenance, the production and maintenance of polarial and toroidal field. Now let's see the stable solar dynamo model. Stable solar dynamo model is the hybrid of the Babcock-Leighton dynamo, which is 2D on the radial and latitudinal, and the surface flex transport magnetic field model, which is also 2D, that in the longitude and latitude. So the stable, as you can see here, is an acronym of the surface flex transport and Babcock-Leighton dynamo. This is a fully 3D Babcock-Leighton dynamo. and it solves the kinematic induction, the MHD kinematic induction equation in a 3D rotating spherical shape. And it uses, as a source term, we use a path maker algorithm as a source term for the colloidal field or the bipolar magnetic active region. So this induction equation, the time evolution of magnetic field with interaction with the velocity field, and this is the advection term, and this is the diffusion, the turbulent diffusion. This is the turbulent diffusion, and V, the velocity field, consists of meridional circulation, differential rotation, and bipolar magnetic regions, or BMR inflow. We'll describe it. This consists of the three components of the velocity field. Here, these are the dynamo ingredients, the mean flow, that is the differential rotation and meridional circulation, and the turbulent diffusivity. The first panel, differential rotation, which is fast at the equator and slow in the poles, and this is the meridional circulation. The blue shows that the streamlines of mass flux, which is counterclockwise, the blue, and the red is clockwise. That means we use two stages of meridional circulation. And the turbulent this is the turbulent diffusivity we use in our model. The source term for the polarized field is an explicit emergence of sunspots or BMR, the BMRS at the surface, at the photosphere. And this shows that white is radial magnetic field outward, and the blue or dark blue shows that the inward radial magnetic field. To place these spots or the BMRS, we use a spot producing magnetic field at the base of the convection zone, which is in a thin layer at the convection zone, at the base of the convection zone. So this spot maker, in order to place the spot maker at the surface, we use a threshold value. When the threshold value crosses the dynamo generated magnetic field, we place a spot on the surface at the photosphere. The content of the flux at the photosphere is also determined based on observation and long normal distribution of magnetic flux to determine the content of the flux at the surface. Once we determine the magnetic field at the surface based on observation, and we extrapolate it downward to a penetration radius 0.9 solar radius. So, in addition to the threshold value that determines the spot placement at the surface, we use also a time delay between a spot maker. This time delay is determined by the long normal distribution function. The probability density function is given by this equation, and the timing is determined by the toroidal field, the dynamo generated toroidal field at the base of the convection zone. So we do have two constraints. One is the threshold magnetic field strength at the base of the convection zone, and the other is the time delay between successive spot emergence. So this shows that this is when the stable produces successful basic features of the solar observation, like this butterfly diagram and sunspot emergence. So then, after this, I am going to present the converging flow into active regions. And again, I'm going to use interchangeably CMR inflow and converging flow into active region. So
Can I ask a question?
good.
When in the slide before, I would have expected the appearance of sunspots to be hemispheric, symmetric from hemisphere to hemisphere, because the setup seems to be perfectly symmetric. Did I miss something, or is it not symmetric? So the meridional flows, there's a symmetry between the north and the south atmosphere. Like everything in the setup looked perfectly symmetric between north and south.
Right, but the spot emergence is not really symmetric actually. So when the halo polarity and Joyce law, we consider this, but they are not really synchronized when it is emerged to the surface, the spots.
But in the previous things, you were saying that you get, it's when it's the threshold is crossed where the strength of the toroidal field at the base of the convection zone, you place it, but it could be crossed by like a range in latitudes and longitudes, right?
Right.
So the location that you place it up above is not necessarily, Mark's saying something.
Yeah, it's not symmetric, you say.
There's no imposed symmetry other than the flows. Okay, thanks, Mark.
Yeah.
I have another question.
Okay.
So when you produce the source, the spot maker, when you make a spot maker, when you have emerging fields, you create a whole 3D field for that, corresponding to that emerging region, do you?
It is.
You put it, the whole 3D field into the domain when a spot appears.
When
Do you put the whole 3D field? Because it's going to be like a omega tube, right? You put that in, or you just put it. I mean, I'd imagine it's difficult to put just some surface field. It has to be because you are a 3D model, right?
it is 3D model.
So that spot, yeah. I'm just saying, how do you put the spot maker? The spot maker is a 3D field. You just plug it in when. Is that right?
It is 3D, so that means, but when it is at the surface, it is only.
Only at the surface?
But maybe you had to figure 3 slides back, I think, right? One more.
Put a
Sorry.
whole 3D field. I think you do put a 3D field, right?
No, sorry, it was forward. Yeah, you missed it. You showed us a picture of the extrapolation down from the surface.
Okay. So that was, so it is a loop. Okay. So it's like a 3D structure. Okay, I remember that. So, okay, so this is your spot maker. Is that
This
right?
is the spot maker. That shows that the underneath shows that.
Marcus raised their hand. Okay.
Speak up,
Yeah,
Mark.
the assumption is that it decouples from the Babcock line wherever it originates. So this is essentially a 3D generalization of the alpha effect that's been used in Babcock-Leighton models for decades.
Okay. Now let's see the converging flow into the active region. So in addition to the differential rotation and the meridional circulation, the active region has established an internal circulation within the active regions. It's the converging flow into the active region, or BMR inflow. So this is observed. So variety of helioseismic observations have detected and analyzed this is especially extended converging flow into the active region with amplitude of 10 to 30 meters per second, and they can also extend 30 degrees away from the center of the active region. This converging flow is due to the cooling of the sunspot or active region. This is enhanced due to the induced enhanced radiative cooling. This shows that the side view of the inflow, as you can see here, there is a surface inflow here, and the surface inflow is manifested by in a certain depth. It is an outflow. It is an outflow due to the conversation of matter, actually. So, what is the implication for the dynamo? This converging flow, that means within the active region, they squeeze the opposite polarity magnetic fields together. That means when, as we know, the following and leading spots, it squeezes them. So it prevents the following spot from going to the pole and the leading spot from going to the equator. Due to this, there is a flux cancellation within the active region. This process leads to decrease the amount of flux within the active region. So this process also influences the build-up of or the production of palladial field and also the polar field build-up. And in general, it can influence also the solar dynamo operation, the overall solar dynamo operation. This is the mathematical formulation of the inflow. This is this equation shows that the temporal variation of the inflow is directly to the directly related to the surface magnetic field distribution. And in our model, the surface magnetic field distribution is the radial magnetic field. So the flow field is directly proportional to the horizontal gradient and absolute value of the magnetic field. See here, the proportionality constant controls the speed of the inflow, and sine theta over sine 30 is that suppresses the unrealistic flows at the poles. And now taking the absolute value of radial magnetic field and smoothing it, the inflow promotes flux cancellation. As you can see here, this is the surface magnetic field with high polarity and Joyce law, surface magnetic field at the photosphere. And when we take its absolute value, it becomes like this. But the inflow velocity, the inflow velocity field is given by this. When we take the, which is proportional to the gradient and smoothed absolute value of the surface magnetic field given by this inflow. Okay, now after some mathematical simplifications from the beginning, we say that the horizontal the horizontal flow at the surface is proportional to the gradient of the radial magnetic field. After some mathematical simplification and considering the mass flux in terms of palladial field at the surface, we can determine the three components of, or the three-dimensional components of the inflow. This is the radial component, which is three-dimensional, and this is the latitudinal component, and this is the longitudinal component of the flow for the inflow. Okay, let's illustrate this long equations in terms of these figures. The radial component shows that here the black is the downward flow, and the image, the white around the black shows that the outflow. And this is at different choice of radial depths. this is at the surface, and some deeper down at 0.96 solar radar, and this is at 0.92 solar radar. This is for the radial component only. Let's look for the longitudinal component. That means latitudinal component. This is for the latitudinal component. This is at the surface panel. The left panel is at the surface, and this is somewhat deeper down at 0.6 radar. But the right panel, if you recognize the color, it reverses. That means the inflow at the surface is outflow deeper down. Let me remind you with this figure. So the surface inflow is a manifestation of outflow in a deeper down. And similarly, this is the longitudinal component of the inflow, that it reverses the inflow at the surface, and so reverses deeper down at 0.92 solar radar. Okay, saying this, this shows that the demonstration of Babcock-Leighton process, and with one BMR at each hemisphere, and the radial magnetic field, or the BMR emergence, is at 25-degree latitude in both, which is symmetric in both hemisphere, and due to the differential rotation and meridional circulation. The meridional circulation actually takes the production of polarial field to build the polar field up. That's the net polar field build up at the end, which is for one BMR at each hemisphere. So this shows that the polar build up, polar field migration. And let's demonstrate the inflow into the surface meridional flow. This shows that the blue dash curve is the meridional flow without inflow. When we include the inflow, the variation around the blue curve shows that due to the latitudinal component of the flow, if you remember this equation, this is the latitudinal component from the inflow, and the variation along the blue curve is, this is from 2 BMR, one in each hemisphere. When we consider many BMRs, this shows that the variation along the black curve is with many BMR, and the gray is due to the introduction of latitudinal flow on the inflow with 10 meters per second, the speed of the inflow here, and we will see other factors. In this figure, we did a parameter study to identify the factors that has most influence on the efficiency of polarial field production. And the polarial field production, if you look at the stronger inflow, the most flex cancellation that shows that reduces the polar field buildup. And we also did a parameter study due to the smoothing of the degree of smoothing. That means the degree of smoothing means from the center of the active region, when we take the area that we smooth out, that has also an influence on the polar field buildup. So this polar field buildup is with different choice of inflow velocity and with a different choice of area of smoothing. Okay. So now I'm going to present the simulation or the magnetic cycles with many BMR. So the MHD induction equation admits exponential growth or decay for the kinematic dynamo. That this equation admits exponential growth or exponential decay. So in order to stop the exponential growth, we need something to stop the exponential growth in this equation. So what could limit the dynamo growth is one possible solution is the magnetic field dependent inflow. The inflow with a nonlinear feedback process. And the other question we are going to ask is that is this inflow sufficient to halt the dynamo growth, to stop the dynamo growth, and to produce a stable solution for the dynamo? And we will answer this in the next slides. So in our previous Babcock-Leighton dynamo, we use a simple quenching term like this. We introduce a simple quenching term that limits the dynamo growth, like in our previous paper. But now the inflow, we find that the inflow can act as a dynamo quenching. So another alternative dynamo quenching is the tilt angle saturation mechanism, or the tilt angle quenching. That is, remember that this is the natural or the Joyce law. This is actually the in terms of colatitude. And that means the tilt angle is produced due to the torque induced in the Coriolis force acting on the rising flux. But if we have a strong magnetic flux, the torque doesn't get enough time to tilt the flux, and that means this equation stabilizes or the B-sat saturation here, that makes it flatter and promotes flux cancellation. This is as a dynamo quenching. So this is from the tilt angle saturation dynamo quenching. We reproduce it in order to facilitate comparison with inflow quenching stimulation. So this is the first panel. The upper panel is mean radial magnetic field at the surface, or at R is equal to the solar radius. And this is the polar field above a latitude of 70 degrees. This is the toroidal magnetic field, and this is the amplitude or the average of toroidal magnetic field with respect to time. Our new word, which is the magnetic field dependent inflow as a saturation mechanism. What we did here is that we turn off the tilt angle saturation mechanism. Instead, we use the inflow as a saturation mechanism. All parameters are the same, and we use only 10 meters per second as inflow speed, but still the natural tilt angle, the Joyce law is there. So when we compare the amplitude of the polar field buildup, you can see that this is around 20, as you can see here, but its amplitude is much decreased here. The amplitude is much decreased. That means flux cancellation is enhanced, and this color shows that it is. Basically, that means the number of sunspots are decreasing, and weaker polar field build up, and lower amplitude of the solar cycles, or the build up of polar field. Okay. Let's compare the two saturation mechanisms, the tilt angle dynamo saturation and the inflow dynamo saturation. This comparison is actually, if you remember, this is from 460 up to 600. So that means we are going to compare 140 years in the cycle is in a 140 years of time. In the tilt angle dynamo saturation, the average cycle period is 10.5 years, and its corresponding inflow dynamo saturation is 12.5 years. I will describe what makes it longer in a minute, but the reversal, the number of reversals in the tilt angle dynamo is 14, while its corresponding number of reversals in the inflow dynamo saturation is 11. So remember that here, even the toroidal field at the base of the convection zone is decreasing. That means when the toroidal field at the base of the convection zone gets weaker, the time increases. The time increases. That is the reason we got 12.5 here for the reversal. In the inflow dynamo saturation, we got 12.5. That means when the toroidal field at the base of the convection gets weaker, the polarial field production also slower, and we got polarity, long polarity reversal. We have said that we use 10 meter per second inflow amplitude, the speed. But when we see the maximum velocity, the inflow velocity, it shows that around 20 meters per second. This figure shows that around 20 meters per second. That means the inflow we use is directly proportional to the radial magnetic field. So it depends on the magnetic field, on the production of magnetic field at the surface. So it's not how much we use an input, it depends on the magnetic field. So the inflow is dependent on
that. Also found in observations of active regions.
Right. It depends. So we know that the active region is with strong magnetic field. It also depends on the magnetic field, the intense magnetic field.
Well, yeah, I'm interested whether nowadays with 24-hour coverage should be possible to extract a similar curve out of active regions and their development.
The observation.
In the observations, yeah. Well, in our case, we only consider the active region magnetic field, but out of the active region, it may be also depend on the magnetic field. All right. So, and when this figure shows that the number of sunspots, the monthly sunspot, heliospheric smoothed sunspot numbers, So the left panel is from the tilt dynamo saturation, and the right panel is the inflow from the inflow dynamo saturation. One is we get a weak polar field, which is the budget for the subsequent flex emergence, or for the that is the budget for the toroidal field, and we can also get a weak or reduced small number of sunspots in the inflow dynamo saturation, because if you remember here we got a very reduced toroidal field, and that is directly proportional, or that is the budget for the next flex emergence. And the other striking result we got is if the inflow is too strong, total dynamo shutdown can happen. This is with 30 meters per second, so it kills the whole dynamo operation. It kills the whole dynamo operation. And that means observation shows that it is almost 10 up to 30 meters per second invert from the helioseismic observation is more than enough to sufficient or to saturate the dynamo, or it impacts or it kills the dynamo as a whole, as you can see here. The future work I want to engage in is that on the coronal magnetic field. The magnetic field we observe on the photosphere here and spread this to the corona is linked to the solar dynamo. And the solar coronal evolution varies with solar cycles as well. That indicates that the evolution is governed by the solar dynamo in the solar interior. So the sun's magnetic field, surface magnetic field, especially the polar field, sets a boundary condition for the corona and for the coronal magnetic field and the heliospheric magnetic field. And the stable model produces the most prominent, the basic prominent observations or figures like the butterfly diagram, the sunspot emergence, and other basic figures. So we can use it as a boundary condition to determine the coronal magnetic field, which is the upper boundary condition of the stable can be used as a lower boundary condition for the corona. And that means this figure shows that the surface magnetic field at the photosphere can be used as a boundary condition to determine the magnetic field at the corona, and the potential field source can use it as a boundary condition, as a lower boundary condition to determine the magnetic field topology in the corona. And actually, the potential field surface source of the Marc Doreza uses the coronal magnetic field only, but in order to determine the UV images, the brightness, we are also going to use the forward modeling to determine, to compare to the observations, the UV observations. This is the coupled strategy. We use stable boundary condition to determine the PFSS extrapolation to determine the coronal magnetic field, and to compare to the UV. This is the simulated UV we can determine here, that shows that this is the open magnetic field, and we can also determine here the open and closed magnetic field from the coupled strategies, the stable, the PFS, and forward model. This is within this solar disk that shows that the SDOA IA 193 angstrom synoptic emission, and this figure both shows this is the Carrington longitude, and we can also determine the open and closed magnetic field from the simulated magnetic field by stable. This is simulated EUV emission. And the other feature plan is that the coronal hole position and lifetime is significantly on the time scale of months to years, as the UNIS 2023 determines that. So we need to run parameter study that we can also determine. We can also determine with different quenching mechanisms. It can be the tilt angle or the inflow quenching. We can examine the distribution and lifetime of the coronal holes as this. This shows that the butterfly diagram, the coronal hole, the hemispheric pattern of coronal holes, and we can determine with different choice of parameter study, whether with the tilt angle or inflow. So that will be the future plan to determine the coronal holes from or constrained on a stable or Babcock-Leighton dynamic. Conclusion: the converging flow toward this active region is an observed phenomena, so we cannot ignore it. It is an important or essential parameter to study in the Babcock-Leighton framework or stable dynamo. So this has a substantial effect on the global solar cycle of the framework of stable, and we observe that, or we determine that flex cancellation within the PMR inflow, and it also affects the production of polarial field, polar buildup, and it determines the amplitude of the subsequent cycles as well. So this converging flow can be also useful on their own to regulate the amplitude and the period of the solar cycle. So in addition to this, we can also, it is also important, or we can determine, we can study the coronal magnetic field from the stable simulation, from the simulated photospheric magnetic field of stable. So this work is already, well, not the coronal one, the inflow, the converging flow toward this active region. We have already submitted it. It is, you can find it on the website. Thank you very much.
Thank you, Kim-Fei. Time for questions.
Just have a comment. It's really great result. And I'm, a week ago or 2 weeks ago, the person gave a talk. So Sharon gave a talk on active region inflows as a dependence on. Will you depend on active region properties? It's inflow measurement. They Sushan. It was like the inflow amplitude is proportional to the unsigned flux. That was dependence.
Yeah.
Unsigned flux determines the inflow amplitude is most sensitive to.
Well,
it was based on. Is it right? I mean, did you include that into your model? That observation.
So if you remember this equation.
Yeah.
the inflow is the proportional to the surface magnetic field distribution.
Right.
Right.
So he's talking about unsigned flux of the region. So this probably is related in some way to that unsigned flux of the actual region. Probably because it's the flux density you're measuring. So
Right. So
your BR max absolute value, right? Is that?
this is the absolute value, but when we consider the sunspots, we know that the magnetic polarity, we need.
Yeah, you use unsigned flux. Yeah.
Right.
Yeah. Okay. So that's consistent with that observation.
It's consistent with observation.
Matthias.
So your dynamo solutions, they're pretty stable. The variability from cycle to cycle seems to be very small. I was wondering if you can kind of push these sort of dynamos with this non-linearities in more variability, a little bit more similar to what the sun is doing, or would you need some other mechanism to lead to more variability?
Thank you. Yeah, actually, if we consider the variation around the tilt angle, if we include the variation around the tilt angle, we can find the variation of the sunspots. They could be similar to the observation, but I didn't consider it here. But for the future, I would like to consider.
Okay.
Just before Michael, Mark Mies typed into the chat and he said it would be straightforward to use Sushant's parameterizations for inflows in this model.
I haven't figured out yet what did the trick to land close to 11 years in the period. So as I understood it, and please correct me if I didn't, you have a 3D model of the solar convection zone, and that runs with what we believe is realistic differential rotation and reasonable stratification and all of that. And then you place at the bottom some sort of magic machine that pops out flux tubes. Is that a way of putting it?
It doesn't have it's not a global convective model. It's not like ASH or something right now.
It's kinematic.
It's kinematic.
You just solve the induction equation in 3D.
I mean it conceptual. And then what determines the tilt angle?
Well, right. So this is the spot producing equation.
Yeah.
But it is not. This is at the base of the convection zone, but it's not connected. It's not connected to the surface. Simply when the magnetic field at the base of the convection zone crosses the threshold value, we simply place spots at the surface, and we can impose a parameter to make it tilt in order to consistent with the observation. And when a spot emerges to the surface, the Coriolis force tilts it to the spot or to the magnetic lattice. That is the reason, and we impose it tilt angle.
Yeah, I understand that because there were these models years ago based on thin flux tube rise of from the bottom of the convection zone, where sort of the center flux tube would modeling the dynamics would rise through the surface, and the tilt angle at the surface was produced by the Coriolis forces that was that this thing encountered in rising. So the tilt angle would change with the cycle because the latitude where things were rising was changing. So it's whereas here the tilt angle is, you just used it as a free parameter.
As a model.
Yeah, I'm not criticizing it. I just want to understand.
Yes.
Although for the tilt saturation case, the other one, there is a distribution that depends on latitude, right? So in the case like in the reproduced the tilt angle quenching saturation mechanism, that one there's an imposed dependence on latitude, right?
It depends on right. It depends on latitude. Right.
But not in the other one. Is that right? So in the there's two cases, right? In the inflow case, you just basically put in a kind of a tilt.
In both cases,
in both
cases, it depends on the latitude.
Okay, but in this, right? Okay.
Yeah, because the
Okay.
natural tilt angle, it depends on the latitude. As the latitude increases, the tilt angle increases.
Okay, so that is in both ones.
In both ones.
Okay, thank you.
But we didn't use it as a saturation mechanism in the inflow.
That's all good. I know, understand.
Mark has a question. Mark,
I was just going to clarify. Yeah, the original intent of this was to start at least making this as analogous to 2D Babcock-Leighton models as possible. So in a 2D Babcock-Leighton model, you usually have an alpha effect that is confined to the surface above 0.9 our sun, but it's a non-local alpha effect. It depends on the toroidal field at the bottom of the convection zone. So that's essentially what stable is. You take the toroidal field at the bottom of the convection zone, but instead, and then you put field at the top, but instead of putting the alpha source term, you have this bundle of magnetic flux. And then we didn't include a Joy's law scatter here, but the characteristics of the BMRs, including their timing, their tilt, their flux content, all of that can be based on observations, statistical.
Yeah.
And is it the statistical side that's introducing the asymmetry that Rebecca pointed out earlier? I mean, there's nothing to force it symmetric, but you start out with these imposed flows that are symmetric. So is that why it very quickly becomes truly three-dimensional in the hemisphere? Because the exact placing of these things and the exact tilt and all these things are actually statistical, would you say, Kimpe?
Right.
Okay. So you said they're all log normal distributions?
Yeah, this long normal distributions all works with the main spatters as well, but all depend. As you have said, your question before was this, so we could.
Yeah. Okay.
Right. So
you always have that numerator, and it's whether you put the denominator or not is what makes it.
Just
Gotcha.
get rid of the denominator, but the upper one, we always stick with it. And all the statistical, which is consistent with observation, like the content of the flux, or as well as this one, the theta, the natural theta angle, the Joyce law, and the long normal distribution, the time delay between the spatters, all are statistical. Yeah.
One more, because I have to leave. But if somebody can take over the discussion, I'm fine with you guys staying.
I can ask later. I can ask
No, you can ask now.
All right.
Okay.
But I was just wondering if you can use this model as a, like running in real time as predictive model now. Because if you just continually assimilate the surface observation of these bipolar regions appearing, and you force this model and let it run, and then but constantly assimilating the new observation of bipolar region with the right tilt and the corresponding info which you put in, will it eventually this model run like a dynamo? You know, just running real time. Will it start to follow? I don't know. The dynamo, actual running of the dynamo. Like then will it naturally produce spot inside the interior where the toroidal field is strong enough? Will that critical position be corresponding to the correct one? I mean, what is missing? Okay, you miss convection. That's all you miss. I'm just saying, can you somehow do
I feel like
this?
this is a conversation we should have with Masumi, who I think is here now. Right? Because you're talking about some sort of assimilative process.
Yeah,
The
because because you're producing spots based on what you have in the interior, right? Based on the toroidal field. Say, okay, here it's strong enough, then a bundle, a source of toroidal field there, right? It's a potential field basically. You put in
Right.
a little bundle. It's a dipole potential. But if you keep doing this, will this model eventually follow the real science? I don't know. What is missing? Lots of physics missing, I guess. Convection is missing there, but I mean,
Well, yeah.
but in the interior, I'm just saying, because it is a 3D model. Eventually, will the interior toroidal field, the amplification of it, will it become such that it will start to produce places where the field is strong and will produce to be consistent with? I don't know. Just wild thinking.
Well, yeah, the physics is that method is replaced by the kinematic, which is based on the observations. That's why it's kinematic.
I'm just showing the source, the toroidal field source is observationally constrained, based on observation. I don't know, Mark Marsh, but if you say. So
Yeah, I was going to say that's exactly part of the motivation in developing this model. Previous data assimilation into 2D dynamo models, you take a 1K by 1K surface magnetogram, and you essentially reduce the information content by 3 orders of magnitude if you're looking at just latitude. But here you can assimilate a full, you can do it as a Carrington rotation or something, but yeah, you can assimilate full disk magnetograms. So yeah, I do think it has predictive potential.
Matthias has.
Yeah. So for 2D mean field dynamo models, very often one challenge is kind of to get the parity right, whether you have a dipole or a quadrupole solution. Does your model always prefer the dipole parity, or can it also have quadrupolar solutions?
It has also, but we use a dipole here. But
it's mostly imposed through the initial state, but if you run it for long enough, do you get phase shifts between hemispheres or even transition into quadrupolar, or does the model very strongly prefer the dipole and suppresses the quadrupolar?
We didn't use it parity here, but yeah, we can include that one, but right, it doesn't shift on that.
Yeah, I can comment on that too. Bidya looked at that quite a bit when he was at HAO, and especially with Joy's law scatter. It's surprising that the runs we've done over the years, they do have a surprising tendency for dipole. I don't fully understand why, but we rarely see any quadrupole modes. But we do see, Bidya's run some of these like 1,000 years or something, and we do see very similar to what the sun looks like in terms of hemispheric asymmetry. That some cycle you'll have a few cycles where the northern hemisphere leads, and then they kind of synchronize, and then there'll be 1 or 2 cycles where the southern hemisphere leads, and it kind of switches but resynchronizes itself, and it seems to prefer a dipole mode.
Yeah. The paper in 2018 and 17 with PIDA, it is the delta angle variation and the parity. So, but we didn't include that one here in the inflow. Yes.
What would space weather look like if the sun goes into a quadruple pole?
I guess we.
That's the thought.
Well, that's another thing that Bidya looked at, that he, but by having a lot of tilt angle scatter in Joy's law, he actually found that the thing would go into grand minimum stages and come out. And when it came out, you would have like one hemisphere. There's common situations where you have like spots in one hemisphere, which would be a combination of a dipole and quadrupole mode. And then which is, it's something that there's some evidence that the sun might have done that as coming out of the Maunder minimum.
Very nice work.
Thank you.
Thank you.